work that's being done in the petrochemical and the chemical industry with CFD type modeling efforts. I think PSRI, we're uniquely qualified to do this because we're actually a research consortium. So we have 32 members and it spans the globe with our membership, including some of the large petrochemical companies such as BP, Exxon, Mobil, Chevron, Shell, HP, or now they're TXJ, TXTG, and et cetera. We have Dow Chemical, we have Hemlock Semiconductor, so we have a good diverse flavor. Our thrust at PSRI is we pretty much, most of our work is done doing experimental work. That's kind of our product. We do a lot of modeling in-house because it helps us with our research. And I'll talk a little bit about that as well. But we also help our clients with some of their modeling. In that case, it's much more larger scale type of equipment we're trying to work with. So with that in mind, I'd like to talk about base much. Some of you may be completely familiar with fluidization. I'm going to breeze through a lot of this pretty quick just to get everybody up to speed. I'm going to talk a little bit about the requirements associated with what industry likes to see out of the modelers and out of the CFD products. And then I want to talk about some of the challenges, it's a new word instead of saying problems, that I've seen in the petrochemical chemical industry. And some of it is very benign, but very prolific. And so I've actually included that, even though it seems very simple. And then the others are pretty much what we've been. So the main advantage of fluidization is that if I increase the gas going through a packed bed, I increase it, at some point I'm going to suspend all the particles, all right? And it has a fluid-like behavior, okay? So the big advantage to this is I actually can now move my solids around in a continuous fashion. So catalysts that was once considered not very good because they deactivated so quickly is now a contender. The FCC actually spearheaded all this. This was back in the 40s. Actually, the fluidized cat cracking process is actually a historical landmark in the US, in Baton Rouge, because it was deemed to be one of the two critical technologies that had an impact on World War II. The other, of course, being radar. So if I can move my catalysts around, I can quickly regenerate my catalysts and always have fresh catalysts to do what I need to do. Of course, fluidized cat cracking being one of the big ones. This is kind of basically a 5-foot diameter. What's that? That's about 1.5 meter diameter fluidized bed. It's a semicircular type unit. Just give you an idea of what it looks like in a fluidized bed if you've never seen one in that system. This is Gelthardt Group A material. So these are typically particles around 70 microns. This is actually a fluidized cat cracking catalyst, which we call ECAT or equilibrium catalyst. Fluidization is not new. It's been commercialized as early as the 1920s with classification, and then it just has progressed. Fluidized cat cracking. It's big in the mining industry, especially with some roasting, drying, hydroforming, Fischer-Tropsch, which we've heard a lot about lately. Acrylonitrile is another breakthrough technology. So definition of breakthrough technology in chemical engineering is technology that actually is a must-have technology after it's been implemented. So when Ohio actually developed the acrylonitrile process, which is a fluidized bed process, all the other competitors had to implement something similar. It was that much of a definitive cost savings. And you'll see that fluidized beds, a lot of this stuff has been this breakthrough technology. Polyethylene, polypropylene, of course, using like unipole and spheripole type processes, cold combustion, short contact grinds, better gasification techniques, pyrolysis, and of course lately we've been hearing a lot about chemical looping. And this is just a touch of what we have with fluidization. So just to highlight some of the stuff that's associated with the energy industry, you have cold combustion. It does have its problem that when you burn coal with air, you emit a lot of COX, which we don't want, with nitrogen. You can't separate those two very easily. So a lot of times now what they're trying to do is do what they call oxyblown combustion, where I actually add pure oxygen into there. Now I just have a very concentrated COX stream coming off. They still don't know what to do with the COX, but they can concentrate it that way. But I have to have an air separation plant to make this work, which is very and of course it starts becoming less economically feasible to do that. So one way around that is to do something called chemical looping. Now, this has been going on for a long time, and I think the first commercial application of chemical looping actually was in the 90s. DuPont had the maleic anhydride process, the use of vanadium oxide catalyst, and it really wasn't a catalyst, all right? It was actually a carrier. And so what happens is that if I take my butane and react it with this catalyst, I actually did an oxidehydrogenation step that made basically butadienes, which then went to maleic anhydride. And so the problem is now I have a catalyst or a carrier that's depleted of oxygen, so it's useless for any further conversion. So then I circulate it into a regenerator where I re-oxidize the catalyst. There's been other systems proposed for this. There's a lot of chlorination chemistry where I can use chlorine in there has been processed. There's some propylene dehydrogenation processes now that actually are being commercialized. And of course, the big one with chemical looping is basically the combustion of natural gas, which is very big in Europe. And then in the US, there's some, Ohio State has a LS fan process, which is coal, which it looks very attractive. And the idea here is, again, is I'm using a carrier and I'm doing a redox on this carrier. So it's a metal oxide, oxide usually oxygen, but not always. And I'm going to basically reduce it in the reactor and then oxidize it in the regenerator. And you have this chemical looping process. It's much more complicated than like a combustor, but economics suggests that you can get better yields out of this. So it does look like an attractive process with this system. Unfortunately, it's mostly to the energy industry, which moves very, very slow. Another process is the polycrystalline silicone. So if you're making solar panels, inorganic solar panels, you have to have very high purity silicone to make it. They used to use the Siemens process, which was chemical vapor deposition. Very, very slow, not very productive. And now they have a fluidized bed process in place to do that. It's actually a graphite reactor because it's very high temperature with that system. And then, of course, a lot of now is going into gasification, coal and biomass gasification. So this is a high pressure fluidized bed process. And the advantage, you get syngas out of it. Now, syngas is the basic component. From that, I can actually burn. I can run it into another fluidized bed process, which is the Fischer-Tropsch process, which actually makes higher order alkanes. So I can make C2, C3, C4s, all the way up to C8s, which is what they do in South Africa. If you're familiar with the oil sands in Canada, they have a very large fluidized bed process called the fluid coker. And here you dig up Alberta, you actually extract out the bitumen, and you squirt it into this reactor filled with particles. Now, what you make is two things. You make more coke on the particles, and you make gas oil products, which can be fed directly into the FCC unit. Problem is that my coke particles will get bigger and bigger and bigger, so they take those coke particles from that fluidized bed, they put in another fluidized bed where they burn it with air. Okay, so they size control the particles by the burning of it. It also provides the heat that I need for the coking process in that system. And then, of course, the fluidized cat cracker, which is probably the biggest, the most known application for circulating fluidized beds. There's a whole list of other technologies out there. This is actually a fluidized bed hospital bed. So they don't sell it for home yet, but I'm being hopeful. IKEA's got my bet. So for me, the history of CFD, we were talking about this yesterday. Back in the 90s, you got, badge of honor if you could simulate a bubble. It didn't even look like a bubble because you had the axisymmetric profile, and then of course it migrated on doing jets, and then we started doing cyclones, and then some sort of asymmetric anisotropic hydrodynamics, which means I had to use the Reynolds stress model for turbulence, which now you can use LES. It just slowly progressed it to now we are doing large commercial operations. Okay, so it is actually a tool that is commonly used in scale up in just about any chemical engineering process that involves fluidization. So I can't think of anybody that's not really doing this. Where it's not being used is when there's a problem with the process and trying to figure it out. I see half the companies using it as a good debug tool, and they've been very effective with that. Others, it's a sales job just to get them thinking about it. So, but this is kind of the state of we are right now in that system. This was a work that was done by the Aberdeen group. It was very nice. It talks about, this is basically CFD in general, so it's not just fluidization, but it highlights that the companies, and I'll just make it quick, the highlights that tend to use CFD, I don't mean have CFD, I mean actually use CFD, tend to be what they call best in class. They're the ones that have the best profitability, the best employee satisfaction, best time to delivery, and they're very consistent with doing all that aspect of it. So there is actually real data out there that says that CFD is a tool that has a certain economic advantage for a company to do that. But we're still not using it to its fullest potential. And there's a couple reasons for that. But I think we're at that point now where we're going to start seeing this. And as most companies, we tend to use CFD. The first thing we'll do is, well, okay, let's validate it against something that we have in the plant. We may use it for some troubleshooting. We may use it for scale-up or predicting. And then we stop there. All right. Now the next step is starting to go into more of how are we going to automate it? Can I actually, and there have been a few cases where I've seen this where you use like a fast-forward process control, where basically you take some process change, okay, it goes into a CFD model, and then it comes out with an answer that you make the appropriate changes to in your process. And you're going to see more of this. And companies like UOP, Siemens, ABB, they're all gearing up just for this, right? As we all know, Siemens bought CD Adapco, and that was the reason they bought CD Adapco. So this is kind of the future for that aspect of it. And then also what they're going to do, and here it says it looks like it's in sequence, but it seems to me like it's happening at the same time. We're putting process optimizers around CFD models. And the idea here is that we won't have to think anymore. We just put in some design, doesn't have to be that great, and we click a button and we go away and we come back and it has the optimum perfect design for you, right? I heard that 20 years ago too, Bonnie, right? That was Vision 2020, you remember that? Yeah, that's 2 years. They got a lot of work to do. Anyway, this is kind of what you have for the industry and the nature of it. So at PSRI, well, obviously we don't make product other than technology. So what we usually do is that we address our members. Our members will really guide us on our research. They're actually a part of the process. And we decide what the needs are, all right? And what we'll do then is explore. So actually now we're looking at cyclones. We're always looking at cyclones, oddly enough. And the idea here is that you can actually not have a symmetric design with a cyclone. You can actually have the outlet tube off axis a little bit, okay? And there's been some studies that says that actually is a good deal. And we started saying, okay, let's do the experiments on it. But before we do that, we actually did the CFD on it and say, is this really something worth pursuing? And CFD is the point now, we're comfortable with it now that it's actually going to give us more thought in our experiments before we actually do the experiments. Then we actually do the experiments. And then, of course, afterwards, you don't just give out data, you actually have to do the analysis part of it. And analysis, a lot of times some reduced order model, that's typically what we've been trained in school to do. But now CFD is part of that analysis part too. There's always something you don't understand. Many occasions have actually bridged that gap for us. Good point here is the intrusive probe, okay? This is some work that was done actually with IFPEN. It's actually been published. And we have a fiber optic probe. You guys have heard of these fiber optic probes we put inside these beds, right? 2 fibers, one's a source, one's a receiver. You get back scattered light. When you have a lot of solids, it scatters a lot. When you don't have a lot of solids, it doesn't scatter a lot, okay? So you get a signal. It's not very linear, so you do have to calibrate it, which is the tricky part. But you can also do some sampling. You can do pitot tube measurements and extraction probes to get an idea of what the solids concentration is. You have to just go in there and do sampling radially. We usually do it 7 or 11 positions going across. We do both ways, north, south, east, west, because nothing's ever symmetrical in fluidization. And we got completely different answers. I mean, this is the radial profile we had here. Even the axial profile, which I'm not showing, was different. Okay, but you see here, this is what our probe was getting, and the measured was significantly less, okay? And here is our solids volume fraction. So that's a pretty significant difference that we see there. Yeah. So the idea we had was, what's going on here? We thought we've had, back in the 90s, I think Michel Luge talked about intrusiveness of these probes. And then we said, well, yeah, but these are easy. So we continued using them. And the extraction tube and the pitot tubes, they kind of bend down and come down like that, which is hard to do with the fibers. So we thought, okay, let's do the CFD. CFD clearly showed that what's happening is that you're stopping enough particles on the probe, and they're just kind of spilling over in front of the probe and artificially making the measurements look higher than they actually are. So we just put a shield on it, and we did CFD on that too. It said that it would work, and we actually did that experiment. Here's some of the old data, and then the new data seemed to line up pretty well. So I think I hit the wrong button. So a good example of how CFD can be very helpful. We've talked a lot about gas bypassing. So if you've been familiar with fluidization, I hope by now you're familiar with this concept that if you have a very deep bed or a lot of dense particles, you build up enough pressure at the bottom of the bed, the permeability is not high enough under certain situations that you don't get a fluidized bed. Even though you have a good distributor and everything else, you're going to get all your gas going on one side, and then you're going to have a stagnant bed on the other side. There's commercial units. Actually, Phillips 66 was the first that brought this attention for the commercial unit. They had a regenerator. It was an old style Mark IV generator, which tends to run at atmospheric pressure, and they were seeing all kinds of bad behavior in the regenerator, high ONX levels and everything else. And it was attributed to this gas bypassing. All right. What's interesting though is it's very dependent on fines. So if I have very low fines, I'm prone to gas bypassing. And I have very high fines, I tend to make it go away. And the CFD simulations actually showed this. We're using a code called Barracuda. It's a hybrid code, so it's a MP pick. And this is low fines and high fines. And you can see here we have very significant large defluidized zones in the bed here, and we don't see it here. This is actually the volume fraction. That's 5 seconds near the end. The average of it, and you can see how much more better fluidized this. You can actually see now we actually captured that gas bypassing there. By the way, the nice thing about Barracuda is I actually do the whole particle size distribution. All right, so it's not a particle size. I think Rodney has lots of comments on that one too, because he has a way around that. This is the difference between those two particle size distributions. All right, we're talking about, if you're looking at the DP50, you're looking at a 1 micron difference. All right, and yet you see dramatic differences in this behavior. So interesting enough, what the CFD brought us here is not saying, hey, we validated it, look at that, it's great. It made us understand what's actually going on. And the problem is that fines are the gas manifold, the gas pipeline into a fluidized bed. All right, when you do the calculation, you look at the surface to volume ratio of the particles and associated with drag, fines drag more gas into the bed than actually the larger particles. So if I don't have enough of those, I'm not dragging enough gas into the bed, I'm going to get the gas bypassing. Understanding what's in the CFD model helps you understand physics, whether it helps you understand physics that's there or even physics that's not there. All right, so it's a very valuable tool to do that, which is one of the reasons why blindly using CFD really diminishes how powerful it really can be. It really needs to be taught more in school because you can use this to better understand what the physics is going on, even if it doesn't give you the right answer. Here's another case of strippers. So basically, if I react my FCC catalyst with oil, obviously I'm going to build up a carbonous layer or coke around it. I'm also going to grab some product with it. I can actually do some steam stripping. You can just basically have it go through a fluidized bed, which is not effective, so usually they have some sort of baffles in here. And the interesting thing is that they would actually put holes in these baffles. And you can actually run the stripper at higher throughput with these holes. So this is actually the bed density. And you can see that I can go to much higher circulation rates when I have holes in there. Now, Richard Sr. talks about how the holes allow solids to come down and everything else like that. And we weren't sure about that. So we decided to do some CFD simulations on that work. And the CFD simulations clearly shows that it's not really, the holes are actually purging gas at a more controllable rate. So what happens when I run at very high circulation rates, I get more gas buildup at the bottom, encapsulating underneath these baffles here. All right, these are called Diskin donuts, by the way. And it just burps out. So if you ever been in a pool and you fill up a bucket underneath with air, I grew up in Florida, so we did that. And you see these large, and it's a very, the solids. And when I have the holes in there, I actually have more controlled release of the gas. All right, so I can go to higher circulation rates. Now, at some point, I can still flood the column. It's just that I can go at higher circulation rates to do that. Another thing is standpipes. Now, the standpipes is actually the pump in moving solids around in a circulating fluidized bed, right? I can't just put a pump in there and move it around. Fluidized cat crackers, they move about 10 tons a minute, so it'd be hard to make a pump like that. So we use gravity to do that, okay? So basically, I have solids at still fluidized, not packed bed, but it builds enough pressure in there that I can now use gas to move the solids around. And so the FCC unit is the standpipe. And a lot of the problems that we see with people having circulation rate problems in FCC units are almost always tied to the standpipe. And the idea was, well, we need to keep it fluidized, so we put the aeration in there. So these little aeration ports that are located on the standpipe. And the idea then is that you don't get the packed bed, which seems to impede the flow. And the problem was, now one of my colleagues is Ted Knowlton, and he loves standpipes. We had to do this problem for him. And he was very concerned about it because he couldn't understand, because there's standpipes now, they're 4-6 feet wide, they're huge. So they put a little bit of gas here at the wall. It's not, how's that fluidizing everything, right? So we did some CFD simulations on it, and lo and behold, CFD shows that it does do a little bit of fluidization, but not the whole column. It actually, what it does, it lubricates the wall. All right? And so now we can do a calculation and say, okay, we know how much gas we need to fluidize it, all right? And that's this number here, all right? But we know in industry the practice is usually take 70% of that number. So obviously the theory was not really catching up to what was actually happening. So that kind of rethinks how we want to actually design these standpipes. And one of the cases is like, well, obviously if I'm lubricating the walls, I really have to make sure that I have aeration such that I do that. So putting aeration all on one side of a standpipe is probably not going to solve a lot of that problem. All right, it needs to be dispersed. So now that a lot of times they'll actually have them spiral around like this to do that. And so, and we've done some studies to show the difference between symmetric and you can see how, oops, so this bottom button is what does it to you. Conveniently located the pointer way, and it's like typing on my iPhone. You can see how it lubricates the walls here, and et cetera. All right. So the one that is probably doesn't, this is actually a standpipe that's 4 feet diameter, it goes up 60 feet, so it's a big problem. But my favorite one is, and this is when I first started, cup. So it's right? And it's called the Davison jet cup technique. It's an attrition testing technique. It's pretty much used in the FCC industry. There's no AST method on it. It's just something that goes out. Everybody had their favorite way of doing it, but PSRI, we had a fluidized bed unit, and it was about 12 inches in diameter. And we could never get the attrition, we had 6 catalysts, we could never even rank them in the right order between the two tests. So let's use CFD to understand exactly what those particles are doing in the cup. So we did that. The idea is that at what velocity particles are actually hitting the wall of the jet cup. And this story even gets even more complicated, which I'll show you later. But I did the simulation. Again, I'm using Barracuda. We use basically 2 codes of PSRI. We have Barracuda from CFD software, and then we have CD Adapco as well. And I was like, okay, well, simulation said, more than half my material is not moving in the cup. And being the rather impatient person I am, I call up Ken Williams, who was the owner of CPFD software. I knew, and I said, your code sucks, it doesn't work. And he like, well, how do you know? And so when I was working at Dow, it would have took me 6 weeks to set up an experiment, but at PSRI, we did it in an afternoon. And sure enough, when I did the video of it, half the material in the cup was not moving. And so I had to redesign the cups, and we came up with, and we did a kind of Edison testing, because back then, this was done like 12 years ago. Back then, this simulation took about a week, and I could just make a new cup, and that took a day. So we just did it experimentally, and we come up with a new conical design. Then we confirmed with CFD, because we want to make sure we're in the same flow regime, so we're not doing more fragmentation, doing more abrasion, which was what we. And we went through that whole process with that system. Well, the jet cup, and now we actually sell to our members and stuff, and there's publications on this as well, and we're working on an ASMT method on this right now, but we're using the conical jet cup has given us very good results with that system. And you can see we actually now all our material is actually lining up, which is helpful. Most of other problems associated with it, though. I can't use my data from a jet cup and put it into a population balance model and say, yes, in your big unit, you're going to see this type of attrition. All right, there's a huge gap there. Now, in the FCC world, we already know what's going to happen with attrition, not a problem. But with the chemical industry, it's a big problem. I mean, I've worked on chemical plants, fluidized chemical plants, where they had design problems that were resulting in $30 million a year losses from attrition alone. When we fixed it, it was $100,000. All right, so it's huge. All right, so being able to predict this is very important. Also, to use this tool to debug where the problem is can be very helpful. The problem is with the jet cup, something simple expressions, but we think more mechanistic approach is needed to do that. So we're actually doing some DEM studies on that stuff. This we use CD Gapco, and we already hit a surprise. First simulation, you hit a surprise. Gotta love research. And it said that most of the collisions were particle-particle, not particle-wall, which I never guessed. All right, so I don't believe it. So we did the experiment. We actually put a glass bottom on our jet cup. We ran it. We did particle tracking, and then Casey was the one that was helping us with this. And we were able to actually do a predicting here. You could take the granular temperature or calculate the granular temperature, measure the granular temperature. It can be related to the number of collisions, and lo and behold, it suggests that it's particle-particle, not particle-wall. Okay, it's always at the climax, always at the end, Anyway, so we're still working on this part of it here, okay? We gave a paper at World Congress because we feel we may need some more of a compartmental model associated with the jet cup itself, then isolate the jet. But that's what we're working on with this system. So also, UOP has used CFD. They used actually a Fluent code. They do have their own user-defined subroutines, which actually work quite well. They built the largest circulating fluidized bed to date. Now, that record's going to be broken in November. So, but right now, it's at the top of the riser. It's 120 inches or 10 feet. So that's from the end of that projector screen to about here. And a riser. And they put all their nozzles on the wall on the outside, and lo and behold, they were not getting very good conversions in this unit because, well, obviously you weren't getting the feed throughout the whole reactor, so it wasn't being very effective. It was a typical scale-up problem. And they did CFD on it, and CFD actually confirms, yes, that's an issue. And they actually came in there, they did some radioactive tracking with this system here. The Lute center core that the feed gas was not getting into at all. So they actually put lances on some of their nozzles and put them in, and now they're actually getting feeds going into the center. And actually the unit's been running now for 2 years and running quite well with that system. Another case study here was a study that was done by Technip, which is in partnership with Axens. They're French companies. They were doing this revamp. They came in afterwards, so about 10 years ago. I don't know who did it. Actually, I do know who did it, but I can't say. But they redesigned the regenerator, and so it all went bad very quickly. So this was before 2001, and this is CFDs of that design, and then we did CFD of this design. And you can see that you get a lot of maldistribution of the gases. Everything's going on one side. So all the solids are on one side, all the gas on the other side. As you can imagine, that's not really what you want. So as a result, we had a lot more post-combustion. In other words, the oxygen I'm putting in my regenerator at the bottom is going straight up to the top, and it's reacting with the hydrocarbons up there and make little tiny explosions. See? And who says particle technology is boring? Anyway, they actually did some work here, and what they did is they changed what they call the spent catalyst transfer line. So I have spent catalyst for my stripper, and it's got to go into my regenerator. So it's got this transfer line that does that, and they redesigned it here. They didn't want to have a blind T, and then they redesigned it to this long radius elbow, and they and I've seen this over and over again. They just go by the old convention. You go 5 L or Ds from the bend, and everything is great. And in fluids, usually just gases, that works. But in the world of solids, no. So solids. So what happened was they were pushing all their solids on one side, and they were all gas on the other side. The distributor really wasn't designed for that, and so they were having that kind of problem with that system. They also, another one here, this is actually a CD Adapco where they were actually looking at cyclone designs. And this wasn't, everything was working fine here, but they really wanted to test this optimization technique. We talked about that earlier, where I can actually couple an optimizer around a CFD model to come to design. So they actually have done that here, and they actually went through a lot of different test cases in here. So this is the base case, and they've come up with a more efficient design associated with here with respect to costs. So that's kind of what they're working with. So that's kind of gives you a flavor of what's going on, which at least what I see what's happening in industry. So it is a very valuable tool, and there are a lot of success stories associated with it. But it still has its limitations, all right? One thing is, it's just not fast enough, all right? So I like to say in probably a process engineering development type phase, if it's going to take more than 3 weeks, forget it, okay? Because the project's already changed by then, okay? So 3 weeks is a really good criteria saying is that this is going to be something that's going to be valuable or not. If it takes more than 3 weeks, you're really going to have a challenge trying to get people to really enjoy using this as a tool. You know, reproducibility, of course, it's got to be very high. There's nothing more frustrating than when you load up a new version of the code and you get a different answer. I mean, if the answer is better and you can get a promotion for it, maybe that's okay, but still. But no, that's always a big issue. Usability. You know, companies no longer want to have a dedicated engineer that does CFD. All right? And I don't blame them. I mean, it's a tool. It's not a career. All right? So we should be teaching students really how to handle CFD and the dangers of CFD associated. I mean, we do this with reaction engineering, right? With reaction kinetics. Oh my God, look at the mistakes. Any reason why we have to have a dedicated engineer with that system here. Most of the challenges, though, is the pre-processing and post-processing. Right? The models themselves, the solvers, they're actually getting pretty good. But you know, the gridding and all the tricks associated with it, the post-processing and handling the files and everything are always a challenge. Okay? Okay, I'm not a patient person. When something's not working, I want to call up on the phone and say, hey, what's going on here? And I want someone to actually give me answers. I don't want to submit an email, you know, have and then I say, no, that's not it. Oh, we'll escalate it. And then next thing you know, it's a week, and I have 3 weeks to solve this problem. You've already eaten a week out of this. So that's always a problem. Capabilities, that's a real thing. Multi-phase hydrodynamics, I mean, that's where the real challenges are. Radiative heat transfer, we're getting better at that, but even heat transfer in general, I have some issues with, but that's right now. 5 years ago, I don't know how many papers I saw on gasifiers. They were modeling gasifiers, and they had no radiative heat transfer in it. They actually had kinetics chemistry and no radiative heat transfer, so they couldn't go figure. Reactions, that's a big one, right? Really don't need them for a lot of the things we're doing. FCC, combustion, I mean, let's face it, it's all diffusion limited. So that's your rate limiting step. So I can just, you know, basically I know what my residence time distribution is of the gas or solids. I could probably figure this out. But you gotta sell this. And you know, if you're in a chemical, so that opens up a whole new can of worms with that system. So with that in mind, what are some of the pitfalls to doing? So with the existing, this is actually a real Chicago road. So it's why I have an SUV. So what are some of the pitfalls we have here? And I have cast iron to like easy fix, need to fix, and not sure how to fix. And so, you know, some of the stuff you think, well, this is pretty obvious stuff, but I'm seeing these mistakes. Not just in industry, I'm seeing it in the literature. Boundary conditions, grid resolution, properties, all should be pretty easy stuff to define and use, but it's not happening. Steady state, well, that's a can of worms. Heat transfer, you guys are working on it, and that's a good thing. Drag, collisional stress models, I mean, these are all things you've talked about in the last, well, at least in the last day. I'm assuming it was the last 2 days. I wasn't here the first day. But you know, there's nothing new there for this crowd. Boundary conditions. So this is my biggest pet peeve. And this is PSRI had this challenge problem. We had 3 challenge problems. 2 of them in a riser, 1 in fluidized bed. But the third one we coupled with NETL. So we used their riser, and then we had a fluidized bed problem there. So this is actually published and available. I could never get the right answer using, this is a code called ArenaFlow. So ArenaFlow is a precursor to Barracuda. All right, so this was done back in, I think I did this in 1999, so pretty old. 8-inch diameter riser, sorry for the English units. And I could never get even the axial profile to line up, all right? So the problem was, my boundary condition was this. I didn't have this here, I just had this, all right? Uniform boundary condition coming in. There's no such thing as a uniform boundary condition, not in fluidization, all right? And that's a real problem. It wasn't until I actually added my L valve, which was part of the design, all the way up to the slide valve. Now, I'm not going to get the boundary condition right at the slide valve either. But by the time that sin makes it to where I care about, it's not going to be a big deal. Interesting enough, it wasn't until I actually put aeration at the bottom of my L valve, which was also in the experiment, did this actually line up very nicely. And there's a lot of people out there that are saying CFD doesn't work, and it's because they're not using the right boundary conditions. All right, and I see that problem a lot. So it sounds very basic, but bottom line is I see it a lot. And so we really need to get that message out. This is a fluidized bed thing here. So I did a little, for this talk, I just said, okay, this is a 3-foot diameter fluidized bed. This is actually what the sparger looks like. So it's a ring sparger. We have a couple what we call shrouds coming out there, which that's a good tool for reducing attrition. There's another sparger down here which we're not using, but it was in the experiment, so I put it in. And you could do this a couple of different ways, okay? I can use what I've seen as this uniform boundary condition across the whole bottom. I can just make the bottom of my ring the boundary with this system here. I can just make the bottom of all those shrouds the boundary condition. Or I can use these injectors, as they call them, momentum injectors, all right, and just direct them down that way as well. And here's kind of the results here with that system. So you can see visually there's a difference. I don't like using this here, but I prefer to use comparisons to the real data. So this is the height above the grid. This is delta P over LG. We call that bed density or emulsion density. The units work out to be density. If you have acceleration, doesn't apply, but in a fluidized bed, that's minimal. And so the uniform boundary condition, really awful, all right? And of course, you know, what happens is I really don't have my wall defined very well in terms of the slip and everything else, so all the gas is going to go up to the wall, all right? But as far as the code's concerned, it's working. That's the path of least resistance. In reality, I never have air going right at the wall because I have a weld line and everything else there, so it's not realistic at all. At the bottom, not too bad. You know, but again, it's behaving more like a fast fluidized bed than a fluidized bed. So here's my bed level here. And I shouldn't be in a fast fluidized bed regime, so it's failing. The one where I have a BC boundary condition at the sparger exit seems to line up pretty well, and the injectors line up pretty well. Okay? So again, it's, you know, the problem is that the CFD models have gotten so good that you really have to model what's there now. I lit up, okay? All right, we talked about this. This is the aeration in the standpipe. 4-foot diameter standpipe goes up 60 feet. What's the boundary condition going into a standpipe? I have no idea, okay? I don't know what's coming out. So I actually simulated the whole loop, okay? Because that's the only way I can get what I was getting realistic with that, okay? And so that's kind of what you have to do now. So in terms of grid resolution, we know this story pretty well. This is Sundar, some work that was done, gosh, maybe 10 years ago now, from Sundar. But it basically shows the effect of Sundar. So, you know, if I'm trying to calculate the pressure drop, delta P over L over space, you know, all these kind of work pretty well. But if I have chemistry in here, right? And by the way, diffusion limited, that's my rate limiting step. I mean, that makes a huge impact on that system. Even the way you design the grids, so if I have, you know, perfectly square grids, One of the problems you have with Barracuda is it has a very simple gridding algorithm, so it's not the best. So, but I can do long grids, wide grids to see what happens. And you can look at this, and again, we're looking at the delta P over L and the system here, and you can see the bed height actually changes fairly dramatically depending on how I use my gridding. Same number of grids, but the changing of just the dimensions of them have an impact. So, particle properties. All right. So, sometimes I just need a density and I need a particle size, which I'm not a big fan of. This is actually some work that was done at PSRI, looking at superficial. And this is the percent fines that we have in that case here. All right. The more fines I have, especially for, it happens for Gellhart Group B material, but for Gellhart Group A, it's dramatic. Okay. If I add a little bit of fines to the bed expands a lot. Okay. Fluidization gets better, bubbles get smaller. Okay. And yet I've probably not even changed my DP50. So it's a big deal to get that right. This is the last challenge problem that we did with NETL. So this is some work. This was done with using ANSYS's Fluent. This is using Fluent out of the box. Trying to make sure I hit the right button. Okay, this is the height of the bed, and this is the delta P over L. And you can see not even a fluidized, it's a riser. They've turned a fluidized bed into a riser. All right. Now, using the same code, but using some of the DQ method of moments where they can simulate a particle size distribution, we're getting a much better answer. Sad story though is we gave them a second chance to do better, and actually it came out worse. But that's research. So, one of the things that we have to worry about is why fines are so important is we tend to look at our particle size distribution either by weight or by volume because we get the nice, pretty Gaussian-Lorentzian peak, and we like that kind of stuff. And the truth of the matter is when you're actually doing the simulation, especially DEM and particle MP-PIC and et cetera, it's a fines problem, okay? And so if I have, classic examples, I have a bed of 10% fines by weight, okay? I'm looking at, like, for FCC material, where I define fines, particles smaller than 44 microns, I'm looking at 35 to 40% by number, okay? Almost half the bed is fines, all right? So you have to actually consider it when you're doing CFD simulations of this nature. I think it's important. Particle shape. I mean, right now the way we handle right now the way we handle particle shape is we get this little correction sphericity that we put in front of the particle size, and if you do that, this is looking at the sphericity here. Looking at the sphericity here. All right, this is corresponding diameters, and you can see not even with the terminal velocity is it actually comparing. That's not even 50, that's comparison. So we really have some challenges with particle shape. There are applications, polycrystalline silicone. I mean, some of those products have particle sphericity of 0.4, right? So completely different behavior in a fluidized bed that we can't capture. And the one, if you ever heard of my talks, I always talk about particle clustering. So this is actually some work, we're working with the University of Chicago, Professor Heinrich Jaeger, and this is actually, it's about 300 micron glass beads in a vacuum, a free fall. He drops the camera with the particles, so you see the same thing here. Now, this is some work we did at PSRI years ago, where we actually, and this is with the help of Frank Schaefer, actually, from NETL. So Frank got us hooked on high-speed video. So we have this optical borescope that we designed for the high-speed video. You can stick it beyond the wall into the bed. This is the freeboard, this is the bed. And this is FCC material. It's the most studied particle probably ever in particle technology. And yet a lot of people have no idea that it even clusters, all right? And it's pretty prolific. Worked just fine because the clustering was already there. But now I'm using CFD, all right, which is, I don't want to say it's fundamental because there is imperialism in it, but it's more fundamental, right? And it doesn't have that in it, okay? So when I'm using CFD to model entrainment and it's 100 times higher than what I'm seeing, of course it is. You're not capturing the particle clustering. Interesting study here, though, is They did it with a couple different particles. This is glass beads. Wrong button again. Wow. Why is this not going back? There it is. They did it with glass beads and copper. It comes down, even though copper has more of a cohesion force between itself, the surface roughness was a lot higher, so they linked it towards surface roughness. And then they did a great experiment here. Just because I was like, yeah, material beads, and they put aerosol, which is fumed silica, on the glass beads, and lo and behold, the glass beads didn't cluster anymore either. They did some experiments where they actually energized the surface. I forget what they call this technique. Thermoluminescence, that's it. And basically, they can measure the electrons that are coming off from the band gap. And they did it. They basically counted the number of electrons, and they actually measured how much electric coulombic forces you need to make particles. They said, you know what, we're about 5 times lower than we should have. Something else is missing. So the current concept now is it's not just electrons that's causing electrostatic behavior. It's also going to be hydroxyl groups or ionic groups of some sort, probably hydroxyls. Now, I did in previous life, I was in graduate school, I did work in surface science. Long story how I ended up here. But I mean, water coats a surface of material at 1 times 10 to the minus torr, okay, in a second. All right, it's everywhere. All right, so you have to consider that. So why does rough particles change all this? And so we're thinking it has to do with a momentum exchange. Smooth particles, you have particles are rotating while they're moving, all right? And there's one of my favorite papers is one of yours where you did the DM study with particle rotation turned on and off. And so we're thinking that what's happening is as the particles collide, if they're smooth, it's just some slip. If they're not and they're rough, you get enough of a change in here. And he did a nice thing here is where we can see particles trying to cluster together. There are 2 particles here that obviously don't like each other. And then this is my favorite one here. It's not rough, but it's not spherical. And you can see how that rotation just really pulled. They wanted to come together and it just pulled them apart. The next thing I want to talk about basically is steady state. I'm not going to really dwell on it that much, but when do we reach steady state? So when when we run an experiment at PSRI, we go in there, we turn on the unit, run it for an hour, we're ready to go take experiments. And then I'm looking at 25 seconds CFD, right? So it's a real problem. I know some people there's some companies that have huge clusters of computers, and they're bragging that they've run for their large FCC unit, we're doing 2 minutes. And I'm like, it's nice, but. And one of the issues that you could have too is how do I get from, at rest, because it's a transient problem, to where I'm having. A stripper is a classic example. Do I start the stripper full? Do I start it empty? And I have to get to that behavior. And it was a real challenge to that. So the folks at CPFTC did a nice job of actually having boundary conditions that can tie and loop around and actually get to that case a little faster. And where we couldn't actually have good results before, we actually had finally some fairly decent results there. Not saying we were at steady state here, but we were closer than we have before using the looping boundary conditions. Heat transfer, I've talked about it a little bit. This is just a calculation that shows you that basically, wind is, if anything over 600 degrees C, you probably need to consider radiative heat transfer, all right? It just has to be considered. It's something you cannot ignore, all right? This is some heat transfer coefficients out of the literature. I love these type of things. You can just pick mass transfer or pick whatever transfer you want, and you're going to get the orders of magnitude changes in behavior that probably happen. On here. In fluidized bed, we have some relationships for heat transfer, but I don't think we have yet a good enough handle on it. Drag is my classic, here's some drag laws here, where I just basically change the temperature, change the pressure, the shape factor, and the volume, and you're seeing, honestly, guys, I can get whatever answer you want just by changing my drag, right? And so we don't have a good physical reality on how to define the parameters in the drag alone. I'm not even saying the drag are actually good associated with the drag. And in the area of fluidization, it's a drag-dominated process. We have to worry about that. So there's some good work being done there, and I'll get into that. But see here, this is something that was published back in 2011, where you can see, basing on the various drag laws, I can pretty much change whatever behavior I want. Here I took the when and U, and I just put a multiplier in front of it, and you can see with just even small changes in the multiplier, dramatic differences in behavior inside a fluidized bed. All right. Fortunately, what I'm seeing people doing now is they're tuning the drag to their problem. I don't have a problem with that, but you need to actually have more data available to make that work, okay? And that's something that needs to be taught, all right? You do that in kinetics, right? You come up with a kinetic model, and then you put in the intermediates to see how you test the model. And we need to do that. And unfortunately, I'm seeing some real problems happening where they don't do that. Now, another really good drag law that we have is the EMS model. It takes into account so-called for clustering and everything else like that. But again, also, it could be very sensitive to have with the system here. So it really depends on your case. Casey's going to talk a lot about drag on Friday, Casey? Yeah. So, but basically what we have is that are we really using the right drag correlations? I mean, I know there's some work that was done out of the Kuiper's group, using lattice Boltzmann and everything else, which I think shows great promise. But most of the stuff that we have is just coming from empirical correlations, either from a single particle or a bed. And then, of course, when you look at the range of interest that we're in with respect to that drag coefficient that you come up with, it's the one that has the most uncertainty. All right, so that's one challenge. The other challenge is that we're pretty good at determining what the drag is for packed bed and for a single particle. And oh, by the way, we're in the middle here. All right, so that's a real issue. Now, the way to get around that, there's some subgrid models. Basically, we kind of precondition the drag to account for that. The mesoscale, as everybody's been talking about, to handle some of that aspect of it. And then, of course, this is a classic case. This was done in 2001 where they looked at this. This is some of Sundar's work, where this is a homogeneous drag model, and then this is with the filtering in there, et cetera, the subgrid model associated with it. Okay, but it's very system specific. It takes a lot more development time to get there, and that's something that needs to be taught. The EMS model is probably, because there's a lot of papers associated with it, and there's a lot of different flavors of it. Here's a sampling that Casey collected of here. And the problem is that, again, like most, it doesn't hit all the things that are important. So this plot here is, what do we care about in a fluidized bed simulation or circulating fluidized bed? Well, we care about the delta P over L. We care about the voidage. We care about the fluxes, both radially and axially, the bubble sizes, right? And we're missing a lot of that. What we do at PSRI, I'm not saying this is the right way of doing it, but we actually, for fluidized beds, we have a little device that automatically measures minimum fluidization, minimum bubbling, bed density in that system here. And we tune the drag to that, and then we use that to solve the larger problem. So at some point, though, you're going more from a model to a curve fit, all right? And you always have to remember that. And it's still not even perfect. So here's some work that we have for entrainment. So we did that. We got good bed density, good bubble size. What's the entrainment doing? Well, this is what it is out of the box here. And it's, this is basically when and U at 1. We like to use when and U with a 0.8 multiplier on it, and it's still horrible. This is another PSRI drag correlation we have here. We have a PSRI correction associated with that drag, so I can actually estimate what the cluster size is and then put that in there. That's still, it's an order of magnitude off. It's better than 100, but it's still not good enough. And if I can just take the drag and just fit the particle sizes there, I actually see that, on average, my clusters are twice as much or something like that. So obviously, there's a mix of the drag, which is limited because you got two different domains, very packed and single particle, and you're in the middle and you're not capturing that. And there's a clustering mechanism going on at the same time. All right, and so that makes it very challenging. By the way, we're not the only ones that are victim of this. This is just simple entrainment correlations, nothing to do with CFD, and you can see they're horrible. So Collisional stress models. Right now, the flavor, everybody likes the kinetic theory. Well, I guess Raphael doesn't like it anymore. But there are always problems that we had with the collisional stresses. Like they said, well, give us granular temperature so we can validate. And that's there. That's out there now. All right. And so we're still not seeing validation done with the kinetic theory. It's still being validated against itself. And I think it's an important part, especially when Raphael was talking about this with the liquid bridging and associated with that. I think she's got it in the right spot. And so this is some work that was done with Frank Schaefer. He came to PSRI. We took our probe with his high-speed camera, and he has a very, very nice particle tracking algorithm that looks at the particle fluctuations, and we can back out the granular temperature. So this is the center of the riser, and we're just dragging that probe out to the wall, and we see an order of magnitude difference in the granular temperature, which is the driver for particles to move towards the wall, which is how the model works. Problem is you have these, I call them macro clusters. Well, the problem is you have small clusters in a fluidized bed, and then you have these streamers in clusters in a riser, and they're probably not. Just like isolate this here, you can do a particle tracking on that system here. And again, we can even get that's what the velocity field looks like, and this is the fluctuations. Again, we can actually look at this at a much closer scale. So I think if we are going to be serious about granular temperature, we really need to take a better focus look on basically how to handle it in terms of validation. And I think we've ignored being able to do the granular temperature probably too long. We can get that data. Here it's the velocity fluctuation in 2D space.
About each box. What's the mean that you're comparing it?
From the time equals 0 state of the particle. Yeah. Well, what? Well, whatever. What's Frank? You don't want to help them with Frank.
No. He says the correlated part and uncorrelated part.
Yeah.
No.
If it is
In
the value normal to the wall, it's okay.
Yeah.
Because it has to be the uncorrelated part.
Right.
If it is the vertical component, then you have it's not just the granular temperature, it's a mixture.
So if your cluster of particles all falling together, they're not colliding. They're compared to whatever you're calling the mean, it'll have energy.
Yeah.
There's no granular temperature. They're all falling together.
Yeah, but it's a localized fluctuation you're looking at, so you're not considering the cluster space around it.
Well, that's what I was asking. So like here you have each box.
Yeah.
You compared.
Yeah, it's at an instant. Yeah.
Okay, so
Yeah. Sorry, I said time equals 0. I meant instant. All right. Yeah.
So then yes.
Yeah. Okay. Yeah. Sorry about that. All right. So anyway, now these are for these clusters and streamers in a riser, and this is actually liquid injection. Actually, we did this project for Syncrude. This was to help them with their nozzle designs, and we have a paper on this actually. And they were worried about cluster formations and everything else. Different kind of cluster, much bigger and everything else like that. But simulating liquid injection to a fluidized bed or a riser, that's something we need, all right? Because if I want to actually optimize my fluidized cat cracking unit, you start with the nozzles, all right? And right now it's very Edisonian, and we don't have a good handle on that. And now, by the way, we used our probe in here so you can see what these clusters look like actually inside the jet, not at the wall and everything else like that. So the question I have is basically at what point can we say the physics is changing with the clusters? I mean, we're going from clusters in a fluidized bed to clusters in a riser to clusters associated with liquid injection. And is it, a lot of times we're fixing these clusters by just changing the drag, but I don't see how that could be drag related unless the hydrodynamics are forming the cluster. And then, or is it with what Raphael was talking about associated with the collisional stress model? I like to think as we do it with the drag, we're being reactive. We know there's a problem, we're fixing it, all right? Where with the collisional stress model, we're trying to predict what's going to happen and be more proactive. So final message, because I'm just out of time, is bottom line, obviously drag models need to be built for faster. Collisional stress models need more validation. Particle clustering, we need to actually take a closer look. And there's a lot of different flavors. We don't have very good nomenclature for this. Microclusters, mesoclusters, macroclusters, I mean, it gets very confusing. And I don't think the mechanisms are the same for all of them. All right? And we need to do a better job teaching best practices because As my advisor told me one time, the most dangerous tool you can give an engineer is a computer. And just to reiterate some of the challenges here, here's a circulating fluidized bed unit. This is the revamp. You can see here, this is my regenerator. These are the, I'm guessing at the loadings typically you see. And you can see if I want to actually model this whole loop, and trust me, that's what people want to do, all right, I'm going to a very wide range of solids concentrations to the whole system. Okay, so sometimes collisional stresses, and it all has to work together. And I don't think we're there yet.